Hello, good afternoon, everyone. My name is Yash Kasundra, and I'm thrilled to present one of my most exciting projects titled Hybrid Optical Radio Frequency Communication Channel Models. So now let's address the question of why we need a hybrid system when we already have an individual communication systems. Well, the answer lies in the limitations of RF communications, which is ineffective in meeting high data rate services that are required in modern day time. So, in response to this issue, a new communication channel system called the optical space system emerged. However, each communication channel performs differently in various different weather conditions. Therefore, our goal for this project is to find the impact of different weather conditions and natural occurrences on these two channels and create a hybrid channel that makes use of both FSO as well as RF depending on different weather conditions. Now, throughout this project, you will be exploring two main terms. First is attenuation, and second is synopcode. So, attenuation refers to the loss of signal strength, while synopcode is a numerical representation of different weather conditions. For instance, synopcode is 0, then it represents clear weather. If it is 3, then it represents dust storms. Moving on to the next slide. So if you look at this, number of sample for both the data set is more than 90,000 samples, which is more than enough to fit any model and do the testing on that. So we won't be required to get more data in this project. Now, in this project, our output variables will be FSO attenuation and RF attenuation respectively, while all other columns will be our features to fitting our models. And since our mentor way provided us with these data sets, there were no null value present at all, because we didn't have to do much of pre-processing at all. So upon comparison, you might have noticed that some of the columns are different in these two data sets. And the main reason for that is RF and FSO are both affected by different weather conditions. So for example, FSO might be affected by wind speed, while RF might be affected by frequency of transmission, etc. Therefore, only those conditions that are some relationship with attenuations were recorded. And if you see, all these features are numerical in nature, except synopcode. So synopcode is the only variable which is categorical in nature, and we'll look at how to deal with that in the later slides. Now let's move on to models. So in terms of models, I started with simple linear regression model to find a linear relationship between predicted attenuation and weather conditions. And then I added some interactions to the model to test how introducing extra features like temperature into wind speed or temperature into temperature, etc., might affect the results. So after testing with different degrees of interactions, I settled on second degree interactions as the performance dropped from third degree onwards. Lastly, I implemented random forest and selected top 10 most useful features based on R square and RMS scores. I basically plotted few graphs indicating that selecting 10 features would yield the best possible results. As for the hyperparameter tuning, I used sklearn's cross-validation library to fit various different random forest models with different combinations of hyperparameter values. And the best hyperparameters that I received from cross-validators was N estimator at 140, criterion at default, max features at square root, and max depth for RF was 125, and for FSO it was 105. So now let's talk about synopcode a little more. So Synop code is represented as an indicator function. So Synop code is represented as an indicator function where it takes value 1 if the event happened, and it takes value 0 if the event didn't happen. So Synop code will always be indicated using this representation over here, and we'll come across this a lot in the result sections when we look at equations for linear regression and linear regression with interactions. Thus, I introduced this term over here to make you familiar with it. Now, I used one-hot encoding to convert Synop code into a numerical variable. This is how I deal with categorical variable in my data sets. Moving on to the performances, measuring the performance of models, I have used R-square scores, which is calculated by getting the ratio of variations to the total variance, as shown in this equation over here. I also used mean absolute error, where error increases linearly with the score, and this error can only be positive. And the main reason is because there is an absolute function present over there. At last, I will be using mean squared error, which is nothing but the average of squared difference between actual and the predicted values, and RMSE, or root mean squared error, which is nothing but the root of MSE. The main difference between RMSE and MSE is that RMSE will punish larger errors more than the smaller ones, while MSE punishes all the errors equally throughout the board. Let's move on to result section. So over here, you can see the two attenuation equations created using linear regressions coefficients and top 15 associated features from our linear regression models. So this equation allowed us to determine which features had the most significant impact on attenuation for both FSO and RF, respectively. And we got that linear regression coefficient, which indicates how much the feature is associated with the attenuation. So if the coefficient is negative, it shows that it is inversely related to attenuation. Now moving on, I also created two more regression equations with second degree interactions, which shows top 20 features and the regression coefficients. So now you might ask a question, how did you choose all these features? Like how many features to keep and which features to remove, and how to make these equations and pass it into our model? Well, I'll explain it in the next slide. So let's take a look at it. The answer to that question was, I plotted R-square value against number of features. Also, I plotted RMSE against number of features. This graph over here is a representation of random forest model, but I did the same for linear regression and linear regression with interaction. So let's take a look at R-square versus number of features graph. So in this graph, as the number of features increases, the R-square values increases up to a certain point. And then it plateaus over a time. And that point at which it stops increasing is our best number of terms that we can keep, or optimal number of features that we can keep for our model or training our model. And now to double check this, we plotted RMSE graph against number of features. So the point at which the RMSE graph stops decreasing and plateaus over time, that's the optimal number of features we need to do. So based on these two graphs, we found that for random forest in RF data, the optimal number was 10, and for FSO, it was 9. So these are kind of similar terms. So we kept 10 number of features for both FSO and RF data. for random forest. For linear regression, it was 15, and for linear regression with interaction, it was 20. Now, these graphs were inspired by a fellow student called named Maitri. Now, let's look at our results, like our error scores. So in this table, I've simply put all of the errors, that is R square error, MAE error, MSE error, RMSE errors for all three models: linear regression with interactions, and random forest. Now, as you can see, linear regression didn't perform very well. The R square value is quite low. Also, our RMSE score is very high. This indicates that our model was not performing too good. But this also helped us in making an interesting conclusion that there was non-linearity in the data. So our data was not linearly related. Thus, our linear regression model didn't perform very well. And this issue can be addressed by introducing some sort of interactions or some sort of human interventions. So thus, we implemented linear regression with interaction. So you can remove non-linearity by converting the features into polynomial equations, which is what we do in linear regression with interactions. But despite this, our R-square error was at 0.7 and our RMSE was at 1.9 for this model, which is not too bad, but it is also not too good, So we still had room for improvement. And thus, I decided to implement random forest to check how the random forest will perform, since it uses decision tree and makes decisions for itself. And the results were astonishing. Like, it performed exponentially better than linear regression and quite better than linear regression with interactions. So R square error was at 0.7 for FSO and 0.6 for RF, which is quite good. Also, the RMSE scores for random forest were very low compared to the linear regression models. So as I discussed, I found non-linearity between our data and then changed it to polynomial form by introducing some interactions. I also found that there was an inverse relationship between distance and attenuation. Thus, I added 1 upon distance column or feature for implementing next models after linear regression. Based on different error scores, we can see that a hyperparameter tuning in random forest gave us the best possible results out of all three models. And thus, we'll be using random forest for this project for the rest of the durations. And thanks for listening to me. And I hope I made myself clear today. Thank you guys, and see you later.